Okay, perfect.
Yeah, yeah.
Please go ahead.
Okay, if you can mute the microphone because I can hear some echo. So
okay.
So then, yeah, thanks a lot. So apologize for not being there with you all. It's really a pity, but I had some other commitment, so I was not able to be there. Sorry for that. Today, in this hopefully half an hour or a little bit more, I'm gonna present the work we are doing in the last month with the team involved in the WP2 of the T-Force project. That may I go ahead? Okay. So I'm sure you heard about the project several times in these days. I am the leader of the WP2 that is in particular focused on the forecasting of the large-scale TID by applying a machine learning model. Here you can see the name and the institutions of all the people involved in the WP. It's a huge effort in a very short time. So I'm gonna show you some very recent results we obtained during this project so far. So we are talking about large-scale TID. I know that you had an entire talk about the large-scale TID. Just to say again that this phenomena is something related to the propagation of a wave-like perturbation in the ionosphere. This is let's say a global or at least a regional phenomena that can usually propagate starting from the auroral latitude down to the low latitude, as you can see in this nice video provided by Cherniak et al. A few years ago. Usually the large-scale TID is something that involves an entire continent. Let's say in our case, we are gonna predict the large-scale TID that is propagating all over Europe. And as you can see from the plot on the right, so basically the phenomena starts from the auroral latitude. So in the second plot here, starting from the 70 latitude north down to the very low latitude. So it's really a huge phenomenon. Why we are interested in forecasting large-scale TID? Because TID is something that is impacting a lot our operational systems and all the technology, especially the ones based on HF and GNSS propagation signals. So usually from the literature, we can see that the large-scale TID is impacting the background electron density up to the 20%, that can induce a Doppler frequency shift up to 0.5 Hertz in the HF signals, and can induce a huge perturbation on TEC, especially a large-scale TID that is from 1 TEC unit up to 10 TEC units. So in several conditions, this could impact a lot the propagation of the trans-ionospheric signals. This is something that I'm sure you know very well, but just to recall the chain of events involved in the large-scale TID genesis and propagation all starts from the energy injection at auroral latitude that occur basically when the solar wind, the magnetic field transport by the solar wind reconnect with the geomagnetic field. So the energy and particles are able to go directly down to the polar ionosphere, increasing the auroral currents. So this increasing in the currents at the auroral latitude reflects into geomagnetic field perturbation that we can detect by using ground-based magnetometer. And then in turn, the energy and the especially the energy involved in the Joule heating at auroral latitude can start the propagation of what we call large-scale TID that we can detect with several methods and several instruments, as you have seen just before this talk with Tony. So in principle, to forecast large-scale TID occurrence, we should start looking at the sun by using the sun images provided by the satellite, looking at the sun, and then we should follow all the chain of events. So the solar wind, in case of solar perturbation and storm that can impact the magnetosphere, disturbing the magnetic field, and then inducing TID in the ionosphere. And in these slides, you can see in red all the parameters and all the instruments we can use to follow this chain of events. So we can monitor solar wind speed and direction in case of especially CME by looking at the image of the sun. We can estimate the solar wind speed and direction of a CME, for example, during a CME, for example, by looking at the image. Then we can measure some parameters at L1, so at the Lagrangian point 1, parameters related to the solar wind and the interplanetary magnetic field. Then we can measure by ground-based magnetometer geomagnetic indices, and so to estimate the currents, basically. And then at the end, we can detect the TID by looking at the ground-based ionospheric instruments, especially ionosondes and GNSS, to look at the ionograms and to the TEC. So in the project, the general strategy we used to forecast TID was to split the problem into 3 different time horizons and 3 different models, basically. The first one is the one that starts looking at the sun. So in case of, for example, a CME, we know that a CME base, depending on the velocity, on the propagation velocity of the CME, can impact the Earth, I mean, from 1 to 2 or few days after the CME leave the sun. So the first forecasting, in principle, could be done by looking at the sun images, and it basically provide the opportunity to forecast large-scale TID with a very high time horizon, let's say a few days, but it is something that is not easy at all. Then we can move to the parameters provided at L1 to try to develop a model that is able to forecast the TIDs with a medium time horizon, let's say from 3 hours up to several hours in advance. And then at the end, we have what we hopefully are gonna develop in this project, that is the model with the highest accuracy, but the smallest time horizon, that is the one based on the measure of basically on the geomagnetic measure at ground that give us the possibility to forecast the large-scale TID from 1 hour to 3 hours in advance. So as I said, in the project, we focus on this very last part of the model. So basically, we used magnetometers data, so geomagnetic indices, in order to forecast the large-scale TID occurrence a few hours in advance, let's say up to 3 hours in advance. So what we can use as features and labels. I know you had a very good talk about machine learning, so I'm quite sure you know that in machine learning terminology, we use the name, we use features to refer to the input to the machine learning model, and the labels to the basically the output of the model, or what we have in our training data set to train the model. So as feature, for our model, we can use the auroral indices, and in particular, we used the auroral electrojet indices not the global one, but the one developed by looking at the measurements from the image network managed by the Finnish Meteorological Institute. So it's basically it's quite similar to the classical auroral electrojet indices, but is in particular referring to the European region. Then we can use TC gradients at high latitude in the European region. Something related to the phase of the solar cycle, so F10.7 or solar sunspot number, then hour of the day, month, and you have already heard about SP-cont, so the spectral contribution from a single ionosonde by looking at the FFT, basically of the last 6 hours of measurements from a particular ionosonde. As label, we can use something that is basically developed starting from the ionosonde measurements again. In particular, we have 3 different labels we can use. The first one is the catalog, the large-scale TID catalog, based on the HF interferometry provided by the Ebro Observatory. The second one is the SP-cont from a single ionosonde, and the third one is what we call HF EU index. That is an index based on all the SP-conts from all the ionosondes in the European network that is able to give us a single number to characterize the whole European region. I go very quickly through this HF interferometry because Tony already talked about it. We are looking at the MUF values from the European network, including several ionosondes at different latitude. And by looking at this time series of the MUF, we can apply a spectral analysis, and we can define this SP-cont by looking at the particular frequency range in which we expect the large-scale TID. And by cross-correlating this information from different ionosondes, we can obtain some useful information about the azimuth and velocity of the propagation of the TID. Based on this SP-cont, we can develop this European index that is basically the average intensity of the TID all over the European region. And by looking at the data, we were, Ebro Observatory actually were able to define some threshold in order to split the HF-EU index into 3 classes. So the first one, up to 0.9, is something that is saying that no TIDs are happening. Up to 1.75, we have, some uncertainty on the presence of the large-scale TID. And for the highest values of the HF-EU index, we can say that the TID is occurring. Problems related to this HF interferometry method is related basically to the fact that under some condition, especially during sporadic E-layer events, we are not able to look at the F layer of the ionosphere by using ionosonde. So we cannot say what is happening in the F layer. We can have lack of data, as for all the instruments we are managing, for problem related to the single station or to the database from which we can take the data from all the stations. Then we have the uncertainty on the azimuth of the propagation of the large-scale TID at the edge of our network, because, as I said, we need several stations to cross-correlate the signals in order to obtain azimuth and velocity information. And then we have some intrinsic delay of the method due to the fact that we are looking at the previous 6 hours of data, and we need a coherent propagation and periodicity in at least 4 stations to say that the TID is happening. The catalog that the Ebro Observatory developed, very useful for the project, let's say, as we can see in a few slides, this is our ground truth for the development and training of the model, is something that is based on visual inspection of the different azimuth and SP count from different ionosomes. And here on the right, you have some videos that is not working. Okay, yes. With two different situations in which in the first one, we have a coherent propagation northeast to southwest over all the ionosomes included in the network. So we can include these events in the catalog because we are quite sure that this is a large-scale TID propagation events. And on the bottom video, we have the situation in which the propagation is not coherent among all the stations. So we are obliged to exclude these events from the catalog. So far we have data starting from 2014 up to 2022 that includes more than 700 TID events. Pros and cons in using the index or the catalog to look at the TID, large-scale TID events. For sure, the index is something that is automatically available, while the catalog needs the human looking at the single events for all the ionosomes to say, okay, we have a large-scale TID events right now. And the cons are basically shared among the two different approaches. So basically, we have no spatial information by looking at the catalog or the index itself. So we should go back to the raw data in order to get this spatial information. And we have some delays due to the fact that we are looking at 6 hours of data to say, okay, a TID is happening. So it's up to you to decide if you want to develop your model based on the index or based on the catalog. And in the project, let's say we are trying to follow the two different approaches. So basically, the NOAA colleagues are focused on the development of a model that is able to forecast the HF EU index. And we at INGV are more focused on a method that is based on the catalog. So the second approach is what I'm gonna describe today here in this talk. So how to model and forecast an ionospheric phenomenon in generally speaking. We have three different approaches basically. Starting from some inputs, we can develop a physics-based model, and this is the best option if we know all about the physics of the phenomena. If we are able to write the equation ruling the phenomena, but this is not the case for large-scale TID so far. We have some black box, so let's say pure machine learning or deep learning model or empirical model. In this case, we have usually a lot of data available, but we know very few about the physics behind the phenomena. And we have something in the middle that includes what we call gray box, that include the physics-informed machine learning model that are a quite new approach in machine learning model development in order to include in the training of the machine learning model some physical constraint coming from the few equations probably that we know about the phenomena, and the explainable artificial intelligence. That is something we are trying to apply right now, in particular to this problem. So something that is based on machine learning or deep learning, but with some techniques that give us the possibility to look into the model in order to explain how the model is able to give some particular output. So generally speaking, to develop a machine learning based model for forecasting model, we have these 4 different steps we should follow. The first one, let's say probably the most important one, is the deep data analysis. I mean, if we have a data set available to train the model, we should be able that the data set is a high quality data set to avoid what we call garbage in, garbage out. So if we put into the model very noisy or wrong data, we cannot obtain a good output from the model. And then we should be sure that the data set is very well synchronized among the different sources. We should manage the data gaps in a proper way. So this very first pre-process, this very first step is quite important to develop a reliable model. Then we should look at the data by trying to highlight the most important features. So we could have, in principle, a lot of different parameters and different data sets, but we should be able to select the most important ones in order to not give to the model unuseful information that can, confuse the model in giving its output. Then we have to split the data set into training and validation data sets. So the first one will be used to train the model, and the second one to validate the output of the trained model. Then we can build here. I report neural network, but this is valid for all the machine learning model. We have to build actually the model and to tune the parameters, so what we call the hyperparameters, so the values that define in details our model. Then the last step is to deploy the model, to evaluate the performance, and to retrain the model when some new data will be available in order to have an update model running in real time, for example. This is a quite important message I would like to pass you. Don't use machine learning whatever it takes. So if we have a very simple problem, we can apply simple model to forecast the problem, to face the problem. So if we have linear dependence among two different parameters, it is completely unuseful to create a huge machine learning model to solve the problem. We can simply run a linear regression, and this probably gives better performance than a complex machine learning model. And the other advantage of developing a simple model is that a simple model is very well interpretable model. That is not true for complex model, especially for machine learning model, even if we have some tools and way to try to interpret the model, the machine learning model. But in case you have a simple problem, try first of all to develop a simple model. This is the message I would like to pass you with these slides. Moving to our specific case, we are developing a short-term machine learning models. So as I said, we are focusing on 3 hours in advance catalog-based forecasting model, looking at the geomagnetic indices, basically. So this is again the details of the catalog we are using. So we have a lot of years available in the dataset, but let's say a lot of TID events, but not a huge number. So we are trying to, especially colleagues in every observatory, to improve the number of TIDs events by looking at new data every day, basically. In particular, our feature so far are reported here. So we have geomagnetic indices, IE, IL, IU, that are the auroral electrojet indices developed by looking at the data from image network, HP30 and SMR, that are basically the KP and DST respectively, but calculated on a huge number of magnetometers, not only the ones that is usually used for KP and DST. And then we introduce some moving averages of those parameters, those variables with different time window. We have HF-related index, so the HF EU index that we use as features, not as label. a single station spectral contribution, so SP cont, azimuth and velocity of the detected TID from HF network. Then solar parameter and solar wind and interplanetary magnetic field parameter, so F10.7, solar zenith angle, BZ, so the north-south component of the IMF, the Vx, so the velocity of the solar wind toward the Earth, and the density of the solar wind. As label, we have basically two classes. So we are talking about a binary classification problem. The zero class that give us, okay, there's no TID happening in the next 3 hours. Class 1 that is saying that a large-scale TID events will be there in the next 3 hours. So first of all, as I said, we should try to develop a very simple model. So let's have a look on the feature space to be sure that there's no trivial way to forecast these large-scale TIDs starting from the feature we are using. What I mean is that basically, if in the feature spaces we have a very sharp separation between the two classes of events, it's completely unuseful to develop machine learning methods or other models. We can say in this, let's say, subset of the features, we will have this class as output. In this other range of feature space, we will have this other class as output. In this case, by applying some dimensionality reduction, we can see here that with two different methods, that there's no a sharp separation between the class 0, that is the blue points, and the class 1, that are the yellow points. So this is why we have developed our machine learning model, trying to forecast the large-scale TIDs in this situation by using these features. So our machine learning stack starts from Python. So we use Python as a programming language because it's open source. It's quite easy from a syntax point of view, and it's one of the top languages for training the machine learning models. Then we apply a cat boost that is very well known gradient boosting on decision trees machine learning model. This is an ensemble model that basically use decision trees as weak learner. So it put together the output of different models. So this is why we call them ensemble model that is based on the decision trees. And the advantage of this, cat boost is a very efficient computation. That is, this cat boost is able to treat categorical and missing value natively. So it's very useful in our case because we are talking about a classification problem and we have some data gaps in our training data set, and then integrates the SHAP values that we are gonna see in a few slides. That is a useful tool to locally and globally evaluate the importance of the single features we are using to train the model. Other tools we can use is the these Optuna tools, that is an hyperparameters tuning tool, very useful to define the details of the model, the best parameters to define the model. And then we use another tools to track the history of the experiment we are running, because as you can imagine, we should run a lot of tries of the model by changing a little bit the hyperparameters of the model. So tracking the history and the performance of the different experiment we are facing, it's quite useful to, at the end, get the best performance from the model. And then we use this Shapley additive explanation framework to explain the feature importance locally and globally in the model. This is something that is, let's say, quite complex from a theoretical point of view, but just to give you an idea on what the SHAP value can do, this is a tool that we can run in parallel with the model. So it's not the model itself. It's a tool that is able to explain step by step, epoch by epoch, the way in which a single feature is pushing the output value to a higher value or lower value. And this is quite useful to locally interpret the importance of the single feature, but at the end, also to globally make a kind of feature ranking. So to say, okay, we have 20 features, but of these 20 features, only 5 of them are really important for driving the model to obtain a very good and reliable output. So this is a quite useful tools. How we split the data set in training and validation data set. Usually what the people do is to take the entire data set and to say, okay, I have these first 80% of the data that I can use for training and the last 20% that I can use to validate the model. This is a very common approach. We decided to use a quite different one. So we run the model on different bunch of data. So here you have 5 different run of the model that use an increasing number of data run by run to train the model and to be sure that the model is not learning from that particular bench of data. So this is a something that ensures that the model is, generally speaking, giving a good output. So, and then at the end we can, I mean, average the performance of the model in order to give some numbers that we are gonna look at in a few slides to define the performance of the model. This is the result of these SHAP values. So here you can see different features we use. For example, this first feature is the IAU moving average on a 6-hour time window. Here we have the HF index, the HF moving average in 2 hours time windows, the solar zenith angle, and so on and so forth. Here on the left we have the basically the absolute value of the mean SHAP values for each features. So this is a kind of classical, we can look at this bar plot as a classical feature ranking. So basically here we are trying to highlight the most important features to be used to drive the model. On the right, we have a quite different representation of the same SHAP values that is giving more details in how each feature is driving the model. For example, here the red points represent the high value of the features and the blue one, the low value of the features. And here we can see how, for example, the HF high values are pushing the output of the model towards higher values, and the low value of the HF index is pushing the output of the model towards lower values. To give you a more clear, hopefully, let's say, picture on how these SHAP values has to be interpreted, here we have a particular case events. So it's the 23rd of December 2022, when at 22:20 a large-scale TID events occur, lasted for 1 hour and a half. So here we have the output of the model at 4 p.m. basically, so before the events. How to look at this graph? Basically, as the output of the model here, we have a number between 0 and 1. We establish a threshold. In our case, it's 0.5. So if the output of the model is below 0.5, we can consider that the model output is the class 0, so no TID are going to happen. If the value of the model is higher than 0.5, we can consider the output as the class 1. So basically, we are saying then that in the last 3 hours, a large-scale TID will occur. So at 4 p.m., we have this situation here where starting from a base value, I don't know if you are able to read the screen here. So we start from a base value that is basically, let's say, the mean of all the output values in the training data set. That is a 0.1 value. Some of the features, so some of the SHAP are pushing the value toward higher value. Some other, especially the HF, that is the most important one here, is pushing toward lower value. At the end, the output of the model is 0.23, so it's below the threshold. So at 4 p.m., the model is saying that no TID is going to happen. Going ahead at 7 p.m., here the situation is completely different. As we can see, starting from the same base values, basically all the features are pushing toward a higher value. So at the end, the output of the model is saying that the large-scale TID is going to happen in the next 3 hours. And this is the truth, because from the catalog, we know that after, more or less 3 hours, a TID will be there. Again, at 22, we have this high value. So the output of the model is the class 1. So the TID is still there. And then after the TID passage, the model is again below the threshold. So no large-scale TID is going to happen in the last 3 hours. So this is a case event in which the model performed very well, and the information was really accurate in forecasting the TID 3 hours in advance. And this is, how we can use the SHAP values to locally interpret the importance of the single features. Going to a global performance evaluation, what we did is to use the confusion matrix. That is, quite very well known. That includes basically the true negative, true positive, false positive, and false negative events among the output of the model. So for us, for example, true positive means that we predict the TID and the TID actually occurred. True negative is the opposite. So we predict that no TID will be there in the next 3 hours, and it actually TID doesn't happen. And full positive and false negative is the two situations in which the model failed, basically. To global evaluate the performance of the model, we can use these 3 different metrics that are the precision, recall, and F1 score, that are quite common in the in evaluating the performance of a model. The precision, you have the equation here, is basically the ratio between the true positive and the true positive plus the false positive. So, and high precision means that we have a very few false positive in our prediction, and this could be an advantage for in same situation. Let's say for monitoring spam email, for example. We don't want that important email will be included in the spam. So we should minimize the false positive events. So we want a very high precision in this case. The recall is actually the capability of the model to catch the true positive among all the positive events, and the F1 score is let's say balance between precision and recall, and it's basically the harmonic mean of the 2 parameters, so precision and recall. In our case, these are the performance. So we have, for the class 0, we have the 0.94% of the model success. And for the class 1, we have the 0.55% of the success of the model. that is not a huge number, but it's something that starts to be useful for a prediction model in a complex problem like the large-scale TID prediction. This is the F1 precision and recall for the two classes. So class 0 in the first column and class 1 in the second one. And as you can see, for the class 0, we are, quite perfect in predicting that no large-scale TIDs is going to happen, but this is due to the imbalance of the data set. So most of the data is basically with no TID, so it's quite expected. And we are, starts to be quite good also in predicting the large-scale TID events. How we can tune our model? Basically, we can move the threshold. We put to divided the two classes, so class 0 and class 1, and we can do it in order to optimize the parameter we are interested in. For example, this is I'm quite sure you are familiar with this ROC curve. That is basically a plot in which you have the true positive rate and false positive rate, and each of these points, drawing the blue curve here, is the performance of the model in terms of true positive and false positive by moving the threshold we selected to divide the two classes. So if we put, for example, the threshold equal to 1, in order to say to divide class 0 and class 1, okay, there's never happened that the model is gonna output a class 1, so we have a true positive rate that is 0, and will never happen that we will have a false positive because we have no positive. So again, the false positive rate is 0. On the other hand, if we put the threshold equal to 0, all the output of the model will be class 1. So we will be able to catch all the true positive, but we have a false positive rate of 1 again. So we should stay in the middle, and depending on what we are interested in, so maximizing the recall or precision or F1, we can establish a proper threshold for our model. So this depends, for example, thinking about an operational way to deploy the model. The single user can define the threshold based on its need, basically. So if I wanna maximize the precision or the recall, I can move the threshold and get the best model for me. How to improve the model? Actually, at present, we are gonna look at the single case events in order to catch when and why the model failed, for example. Here, I wanna show one of the cases in which the model was predicting a large-scale TID. So we got a class 1 output, but we have no large-scale TID in our catalog. That is what we consider our ground truth. So looking at the GNSS data, here in particular on the right, you have the trended TEC kilogram. So basically, it's a way to represent the trending TEC as a function of time and latitude. And you can clearly see here in the first half of the day that we have a clear signature of large-scale TID that is not included in the catalog. We don't know why, but probably in this situation, there were a sporadic E, so we were not able, looking at the HF data, to catch the large-scale TID occurrence. Or probably we had a data gaps problem or something like this. So looking at the single events, we can highlight the cases in which the model failed, or the cases in which the model actually produced the right output that is not included in our, let's say, training data set for several reasons. So this is a very important check and validation we are doing right now to improve the performance of our model. So take-home messages and next steps. For sure, large-scale TID are due to a complex chain of physical phenomena that are very hard to be predicted. So we have no physical model capable of predicting large-scale TID so far. This is why we are trying to develop a prototype model based on machine learning technique to face this problem from an operational point of view. And so far, we face the problem as a binary classification problem, or from the NOAA colleagues, they are trying to approach the problem as a regression problem based on HF-EU index prediction. But I had no time to show these very interesting results in this talk. So far, we developed this gradient boosting on decision tree models that seems to be promising to give us prediction of large-scale TID a few hours in advance. And this cut boost is very useful also because it's giving the possibility to locally and globally interpret the results. And so looking in particular to the impact of the single features on the output of the model from a case events point of view, but also from a global point of view. We realize by looking at these particular case events, so failure of the model, that the use of ancillary data, so that, for example, the trended TC, can be used to identify both the failure of the model, but also some large-scale TID the model is predicting that is not included actually in the catalog for several reasons. For sure, as the next steps, we should identify additional important feature to drive the model, or to perform what we call feature engineering. So to try to put together the features in order to obtain some new parameters that is better capable of driving the model. And then for sure we should include different data to fill the gaps in the catalog, the gaps due to the physical constraint of the HF measurements themselves. So thank you for your attention. I don't know if I was on time, but I guess yes. So if you have any questions, I will be more than happy to try to reply.
Okay. If there are questions, I will probably have to repeat them because Claudio can probably not hear the people in the room. If you have any questions, okay.
Not a question, but
Okay.
a comment. First of all, congratulations. I think this is a very good work. And concerning this prediction that the models say yes, then maybe you can go to the mind.
Yes, that's also possible.
Comment, maybe you can make it easier. Exactly.
No, Claudio, I was telling that not a question, but a comment. Can you listen to me?
Yeah, sure, David. Yeah.
Just to confirm that this prediction of, first of all, congratulations, because you show very nice results. But these predictions that your model say yes, but are not included in the catalog, but are observed in other methodologies, we can put some light here by making a reanalysis and try to explain why these supposed events that you predict and observe in other sensors cannot be are not in the catalog. So data gaps or other kind of stuff. This is the only comment I can say.
Yeah, this will be very useful, and this is, I mean, we are aware about the limitation of the method itself, because I mean we have some physical constraint coming from the measurements. So this is why we are looking at several case events in order to be sure that the model output is not correct, or the events was not detected by the HF interferometry, so not included in the catalog. So I guess this is a very important point for the development of the model, but also for the validation of the model we are developing and you are responsible for. So
there seems to be no further questions anymore, Claudio. So thank you for your presentation.
Thank you. Sorry again for not being there, and enjoy your time all together.